Hey everyone, and welcome to this explainer. I am absolutely pumped to guide you through today's topic. We are unpacking the physics of collisions, and let me tell you, it's a fascinating ride. Whether we're talking about microscopic atoms bumping into each other or a massive everyday car crash, the underlying rules of the universe that govern these impacts are incredibly elegant. Honestly, they're kind of mind-blowing when you really look at them.
I want you to start by just visualizing two very different scenarios for a second. Imagine dropping a super bouncy ball onto a hard concrete floor, and then imagine dropping a lump of sticky putty. One rebounds with almost all its original speed, right? While the other, well, it just goes completely splat. Today, we're going to uncover the exact physical laws that dictate why these two objects behave so wildly differently the moment they hit the ground. First things first, what actually is a collision in the realm of physics? Well, by definition, a collision is the transfer of momentum due to internal forces and mutual interaction between particles. And here is a really cool little detail to keep in mind. Physical contact isn't even always strictly necessary. Literally, two particles can interact and transfer momentum purely through forces, like electrostatic repulsion, without ever actually touching in the traditional sense we think of. Okay, let's dive into this. Before we start splitting collisions into different types, we have to establish the absolute ground rules. These are the laws that survive every single collision in the universe. Provided no external forces are messing with our system, linear momentum and total energy are always conserved. No matter if it's a perfect bounce or totally messy splat, the total momentum and the total energy before the impact will exactly equal the total momentum and total energy after the impact. No exceptions. So, to understand where the energy actually goes, here's our roadmap for this explainer. We'll start with 1, the universal rules, then look at 2, elastic collisions, 3, inelastic collisions, 4, perfectly inelastic collisions, and finally wrap up with 5, the master comparison. Moving right along to section 1, the universal collision rules, where momentum survives every impact.
Here are those baseline laws again. Remember, total energy is safe. The universe never just deletes it. However, mechanical kinetic energy, the actual energy of motion, well, that's the rebel here. The entire primary difference between the types of collisions we're about to explore lies entirely in whether or not that mechanical kinetic energy is conserved during the process.
Which brings us to section 2, elastic collisions, aka the perfect bounce, where we are conserving kinetic energy.
Now, what's really fascinating here is exactly what happens during the impact itself. As two bodies come into contact, they deform. It's just a fact of physics. At the exact instant of maximum compression, kinetic energy is momentarily stored as elastic potential energy. It's basically acting much like a compressed spring. But because these bodies are perfectly elastic, they push against each other and completely, flawlessly regain their original shapes. This converts all that stored potential energy right back into kinetic energy the moment they separate. Because we are only dealing with conservative forces here, like gravity or ideal spring forces, no mechanical energy is lost to things like heat or sound. The total kinetic energy before the collision is exactly equal to the total kinetic energy after the collision. It's a 100% perfect transfer.
In physics, we actually measure the bounciness of a collision using a handy little variable called the coefficient of restitution, which we represent with the letter E. For a perfectly elastic collision, E is exactly equal to 1. Mathematically, this simply means that the velocity at which the objects separate is exactly equal to the velocity at which they approached each other. To really wrap our heads around this, we have to look to the microscopic world. The legendary physicist Richard Feynman hit the nail on the head when he pointed out that collisions between atoms or molecules in a gas at moderate temperatures are perfectly elastic. Why? Because these elementary systems have absolutely no internal gears, wheels, or parts. There's literally nowhere inside an atom for the energy to get impounded or lost as friction, so they just bounce off each other perfectly without losing a single drop of kinetic energy.
Let's step back into our world for section 3, inelastic collisions, the energy drain. Let's see where that energy actually goes.
Notice the stark contrast we have here. While a microscopic gas molecule bounces perfectly, a real-world macroscopic object, like a car or even just a tennis ball, has a super complex internal structure. When these macroscopic objects collide, they involve messy, non-conservative forces like friction. They have parts that bend, break, or vibrate.
So what's the physical mechanism this time? Just like before, we have contact and maximum deformation.
But in an inelastic collision, the colliding bodies just do not have a strong enough tendency to completely regain their original shapes. They might partially recover, sure, or they might just remain permanently dented or deformed.
So the absolutely crucial point to take away is this. Kinetic energy is not conserved here. The total kinetic energy after the collision is literally less than it was before. But wait, remember our universal rule? Total energy is always conserved. So that lost kinetic energy hasn't just magically vanished, it has transformed. It turns into other forms of energy, specifically heat, sound, or internal vibrational energy within the objects. Even at the subatomic level, lost energy might go into ionizing an atom instead of making heat.
Because the objects don't push away from each other with the exact same vigor they had when they approached, their velocity of separation is less than their velocity of approach. Therefore, for almost all real-world inelastic collisions, the coefficient of restitution, E, sits somewhere greater than 0 but less than 1.
Now for the extreme case. Section 4, perfectly inelastic collisions, where things are sticking together.
And this setup brilliantly illustrates the concept. In a perfectly inelastic collision, the bodies have absolutely zero tendency to regain their shape. Think back to that lump of sticky putty we talked about at the start. They hit, they deform, and they simply merge into one. Right after the impact, the two bodies just stick together and move forward as a single combined mass, with a common, shared velocity. What you really need to take away from this is that a perfectly inelastic collision represents the absolute maximum possible loss of kinetic energy from a system, while crucially, still adhering to the law of conservation of momentum. Because the two objects stick together and move as one single unit, they obviously do not separate at all after the impact. Their velocity of separation is a big fat 0. Therefore, for a perfectly inelastic collision, the coefficient of restitution, E, is exactly 0.
Let's wrap this all up in Section 5, the master comparison, bringing it all together.
Let's walk through this cheat sheet row by row, because this is your ultimate study guide. Notice the top two rows. Linear momentum and total energy are completely conserved across the board. The big split happens right at kinetic energy. In elastic collisions, it's conserved. In inelastic, it is not. And why is that? Well, because elastic collisions involve only conservative forces and full shape recovery, giving us an E value of 1. On the flip side, inelastic collisions involve non-conservative forces, incomplete deformation recovery, and an E value of less than 1, dropping all the way down to 0 when things stick together.
I want to leave you with a bit of a mind bender based on what we've learned today. Every single time objects bump into each other in our macroscopic world, a tiny bit of kinetic energy is lost to heat and vibration. If you zoom out and view the entire universe as one giant closed-system pinball machine of constant collisions, what is the ultimate fate of all that transformed, lost kinetic energy building up over billions of years? It's a pretty profound question about the ultimate physical destiny of our cosmos. Well, I hope this explainer brought the physics of collisions clearly into focus for you. If you enjoyed this structured breakdown and want to keep exploring the universe with us, please make sure to like, share, and subscribe. It absolutely helps us make more deep dive explainers just like this one. Keep questioning, keep learning, and I will see you in the next one.